So, oops, let's call this example, I think it's example 4. We're doing examples of applying Faraday's law, and we show an example where the area changed. We showed a couple examples where the magnetic field changes. Now I want to show an example where the angle between the magnetic field and the area changes. So let's just say we've got a loop, a square loop in a magnetic field. Let's just go ahead and say that that square loop has side L, so its area is L squared. Side L, right? So so half L from the dotted line. And I'm indicating that thing can rotate about its center axis. So let's just say it rotates about its center axis at rotational angular velocity omega. That was incorrect. I mean rotational frequency omega. Rotational frequency omega. Angular velocity and rotational frequency have little differences between them. So, oh no, sorry, in this case they're the same. Ugh, gosh. Okay, rotational frequency, angular velocity. Okay, so let's go ahead and figure out what is the current induced, if any, in this loop that is rotating in the magnetic field. Just to make sure we understand, let's go ahead and look at a top view of this. The top view is looking down from above. So the top view, looking down from above, the magnetic field goes along the plane of the page, up the plane of the page, and we're seeing the top of the coil and the single loop. And the single loop is rotating about a central axis so that at some later time, it's going to be at some orientation, right, theta, from where it started. So what's important to note is that when we start, that the loop has an angle of 90 degrees with respect to the magnetic field, but at some point it's going to rotate around. It's going to have an angle that goes from 90 to 0, back to 90, back to 0, back to 90, back to 0. Or you could say 90 to 180 to 90 to 0. In any case, the angle changes. The angle between the loop's area, let me draw the area of the loop, right? The area of the loop points in that direction. So the area of the loop points in that direction. So actually, I should have said, so it was what I said was true, but the angle that we're interested in is the angle between, right? So B dot dA is the angle not between the wire of the loop and the magnetic field, but it's between the area and the magnetic field. So the angle starts at 0 and goes to 90 and goes to 180 and then goes to 270 and goes to 0, right? So the angle as the loop goes around like this starts at 0 and gets bigger until it goes all the way around. Okay, so what does Faraday's law say? So Faraday's law says that the EMF induced. Okay, so what is the EMF or the current induced? If we know the resistance, we know the current. And Faraday's law, N d phi dt. So we just need to, again, apply N d phi dt. N is 1 in this case, remember, but I'll just leave that in there for now. D dt of phi. Phi is the integral of B dot dA. And let me pause for a second. And at any instant in time, B and the angle don't change across A. What changes is they change in time, but they don't change in space, right? That's what's important. At any instant, B, theta, and A don't change, and dA don't, B and theta don't change over A at any instant in time. So this just becomes d dt of BA cosine theta. That's the flux, right? That's the BA cosine theta is just the flux, right? It's the flux at any instant. It's BA cosine theta. Right? Theta is going to be different at different times, but the flux at any instant is the magnitude of the field B times the area of the loop A. Neither of those change, times the cosine of theta. And theta is what changes. So then we can pull out of the time rate of change, right? B and A, they don't change with time. It's just d dt of cosine theta. Theta changes with time. NBA, as in basketball, but that has nothing to do with it here. There's no spherical objects. Okay, anyway. N is the number of loops, B is the magnitude of the field, A is the area of the coil. Those don't change in space or in time at all. But what does change is the angle theta. So the angle theta changes with time. And so what we can write is we can actually take a time derivative of the cosine theta. Time derivative of cosine theta is the derivative of cosine is negative of the sine. Isn't that right? Minus sine theta d theta dt. I believe that is correct. That is the, I believe that's the correct derivative. And if I got a minus sign wrong, I don't think so. Yeah, if I got a minus sign wrong, then it doesn't matter because that just has to do with the direction. And so you can look at this and say, oh, d theta dt is how fast does theta change with time? That's just omega, the angular velocity. So we've got n, b, a, omega, pull the minus sign out front, sine theta. And remember that since omega is d theta dt, and I guess if omega is constant, then therefore theta is equal to omega times t. And I didn't say it, but I should have said at the beginning that theta was a constant. Omega was a constant. Omega was a constant, but we can say it now. If omega is a constant, then theta is equal to omega dt. In other words, it's rotating at a constant rate. It's rotating at a constant rate in this field. So therefore, the induced EMF, and again, leaving out minus signs, I'm going to drop the minus sign just in terms of magnitude, is N, B, A, omega sine omega t, right? So the induced EMF is going to vary as a sine function. The induced current is going to vary as a sine function. N is equal to 1. And then, right, for a single loop coil, or if we had a coil with multiple loops rotating in a magnetic field, we would be inducing a current or an EMF of this value in that loop. And this is what is known as an electric motor. An electric motor is... Sorry, I keep saying things that are only sort of correct. Never mind what I was going to say about the electric motor. What this is sort of the opposite of the electric motor. It is a generator. It's an electric generator, but what this does is it generates electricity. It generates AC electricity because it's going to go forward for half the loop, right? Because sine omega t is going to change in sign, plus to minus. So remember, we dropped the minus sign. So this tells you the induced EMF. So the induced EMF is going to go up and down and up and down and up and down. If we take into account minus signs, it might change the orientation of that sine curve, but it's still just going to go up and down and up and down and up and down, positive to negative to positive to negative, the induced EMF or the induced current. Okay, that's the induced current in a rotating coil. Oops.